factors. Now we head to table 240.6a and we choose the next standard size breaker. And this would be a 400 amp breaker. This would also be a 400 amp service. Let's get to it. Now let's do that exact same calculation but on a three-phase system and show you the beauty of three-phase. What size main breaker would you select for a business with a total calculated load of 95,000 VAs on a 120/208 three-phase system? Step 1, find our total connected load. Well, they've already given us our total VAs, so all we have to do is divide. But with three-phase, there's one extra step. Because of the geometric nature of three-phase, we have to take that 208 and multiply it by the square root of 3. The square root of 3 just so happens to be 1.732. Once we work that math out, we end up with 360.256. And it seems like a lot of work on the front end, but you'll find out that you'll trade this little bit of math for what this is getting ready to provide for us. Now we can take and do our math, and after we divide it out, we end up with 263, and of course we would round up in this case. There are no more demand factors, so we head to table 240.6a and choose the next standard size. And this is where the beauty happens. We're going to now put this on a 300 amp breaker instead of, like in the previous question, it would be on a 400 amp, meaning that we'd have to have larger wire in the previous question, which may lead us to have larger pipe, which we may end up with a larger cost of overall project. The beauty of three-phase is the numbers come down. So this one's on a 300 amp service, which means we can put it on smaller wire, which might mean we can put it in smaller pipe, which might end up having a smaller overall cost. Let's get to it. What size main breaker would you select for a business with a total calculated load of 80,000 VAs on a 120/208 three-phase system? Step 1, find our total connected load. In this case, they've done the work for us. They've given us the 80,000. Now all we have to do is divide. We do our little bit of pre-work and we end up with 360. Now we take and divide that out and we end up with 222 amps. In this case, we'll round down to 222. There are no more demand factors in this calculation. We head over to table 240.6a, choose the next standard size up, and put this on a 225 amp service. That's the end of lesson 8.3. You can head over to electricalexamcoach.com. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And this is lesson 9.1 in our video series. We're going to be in Article 310, and we're going to be learning all about ampacity. Ampacity is the maximum current measured in amperes that a conductor can continuously carry under its usage conditions without exceeding its rated temperature. Everything that we're doing in this program and out in the electrical field is to protect first the people and then the equipment. And it's no different with the wire. This wire is only rated to handle so many amps before the insulation will start to deteriorate, and ultimately we could end up with a fault, short circuit, or just arcing and sparking. With that being said, in this video series, we're going to slow down and we're going to master wire ampacity and how many amps a wire can hold and how to select the right wire for the right load. Let's get to it. Now let's learn about our primary ampacity table. If you're in the 2017, it's table 310.15B16. And in the 2020 and later, it's table 310.16. Same information, new name. If you're in a softbound NEC, these should be your page numbers, depending on what print of the NEC you have, whether you got the first round or second round print, but this will get you close enough. The most important thing is read the title of the table and make sure that it matches the actual table number. Let's get to it. Now there's a lot going on in this table. We're going to slow down in this lesson. This is our ampacity basics lesson. Because if you don't get this, it's going to be hard to have an electrical career. It's going to be hard to ever be able to pass your examination. So we're not in any hurry. If you need to watch this video over and over, you can do it. The first distinction we want to make with this table is that it's actually two tables. On the left-hand side is going to be for copper conductors, and on the right-hand side is going to be for our aluminum and copper-clad conductors. Left-hand side copper, right-hand side aluminum. And if you'll notice, they mirror each other, but in the NEC, it's smushed all into one table. Now let's take a look at what all this information means. Now we're going to do a quick breakdown of the table. We won't stop on any specific part until we need it in the program because I don't want to confuse you. And later you'll understand why I did it piece by piece. But we read all of our tables from top to bottom, left to right. I want you to focus on the left-hand side because that's the copper side, but you'll notice that everything that we do is going to be mirrored over on the aluminum side. So starting at the top, it gives us the scope of the table. We're not going to get into that right now. It comes later in the series. Then you'll notice there's a 60, 75, and 90 degree C columns. Below that are going to be the insulation types like THHN, THWN. On the left-hand side, you're going to have the conductor sizes, which is easy. And then in the middle, you'll find the allowable ampacity for each respective column. Now let's take these piece by piece and explain exactly how to use them. Now let's learn about terminals and insulation rating. And that's where these 60, 75, and 90 degree C columns come into play. Whether we're dealing with terminals or insulation around the wire, each one of them can only handle so much heat safely. Whether it's a lug or a breaker or a switch or the insulation around the wire, they're all rated for specific temperatures. I'll give you a little heads up. Out in the field, all of these are almost 99% of the time rated for 75 degrees C. And the insulation has multiple ratings. Some of them are rated for 60, some of them are rated for 75, and some of them are rated for 90. The reason this is important is it's going to help us choose which one of these columns we select our ampacity from. If the terminals are rated 75 degrees, we're going to choose the 75 degree C column most of the time. I'll explain what most of the time means later in the program, because this section is just like other sections of the NEC. There are blanket rules that apply generally, but later they get modified. But for right now, what I want you to remember is we're going to match the column that we used based off the terminals that the device is rated by. Regardless of what the insulation is, we can choose from whatever column that the terminals are rated by, unless modified by another code. Now let's lay some ampacity ground rules. Unless modified by a specific piece of equipment or another code, these rules will apply generally. If the question states that it terminates to 60, 75, or 90 degree C terminal lugs, you're going to make your selection from that respective column. And as with overcurrent protection, we're going to do 125% demand factor for all loads that are expected to run for 3 or more hours. Remember our continuous load rule? That carries over into wire sizing as well. Let's get to it. What size AWG copper conductor would you select for a 60 amp load using THHW terminating on 75 degree C terminals? Step 1, find the total connected load. Well, in this case, we already have the load. It's 60 amps, but we must check for demand factors. They've not told us about a specific piece of equipment or that it's a continuous load, so there are no demand factors. But we have to learn one important rule for sizing wire. The wire must meet or exceed the known load. There is no next size up rule. The wire always has to meet or exceed the known load. So we head to our primary ampacity table, and we're going to start on the left-hand side because our question is copper. Always carefully go through these steps. What type of metal? Copper. What are my terminal ratings? They are 75 degrees C. What is my known load? 60. I'm going to start down the 75 degrees C column until I find a wire that covers the known load, and then I'm going to use a straight edge to come over and select my size wire. And in this case, you would put it on a 6-gauge wire. We go back and we select B. Great job. What size AWG copper conductor would you select for a 74 amp load using THHW terminating on 75 degree C terminals? Step 1, find the total connected load. It's 74 amps. Now let's check for demand factors. Well, in this case, there's no specific pieces of equipment and there's no continuous load, so there are no demand factors. And we have to remember that our wire must meet or exceed the known load. We head to our primary ampacity table. We make sure that we're on the right side of the table. In this case, it's copper. And we have 75 degree C terminals. So now we take off and find a wire that will cover the known load. We find one that will cover 74 amps. We use a straight edge to come over and tee off at number 4, and we're going to select A. Great job. That's the end of lesson 9.1. You can head over to electricalexamcoach.com for quizzes that go along with these videos and unlimited access to the testing center. Ampacity is one of those topics that you have to take one bite at a time. So don't get overwhelmed. Take your time. I know that you can do it. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 9.2 in our video series. In this lesson, we're going to be sizing wire for continuous and non-continuous loads. Let's recap on the basics before we get started. If the question states that it terminates to 60, 75, or 90 degree C terminals, we're going to make our selection from that respective column under normal circumstances. And the second one is, as with overcurrent protection, like we learned before, we're going to do 125% demand factor for all loads that are expected to run for 3 or more hours. Let's get to it. What size copper conductor would you select for a 40 amp load using THHW terminating on 75 degree C terminals? Step 1, find the total connected load. In this case, we know the load, it's 40 amps, but we must check for demand factors. It doesn't mention a specific type of equipment or that it's going to be a continuous load, so in this case, there are no demand factors. And we always have to remember that all wire must meet or exceed the known load. So we have to find a wire that meets or exceeds 40 amps. We head to our primary ampacity table, and the first thing we're going to do is check the type of conductor. It's copper, so we're going to start on the left-hand side of the table. We're in the 75 degree C column because that's our terminal rating. Then we're going to slide down and find a wire that meets or exceeds the known load, and we find out that it's an 8-gauge conductor. And we select C. Great job. What size copper conductor would you select for a 60 amp load running for more than 5 hours using THHN type wire terminating on 75 degree C terminals? Step 1, find the total connected load. Well, our starting known load is going to be 60 amps, but we must check for demand factors. When we find out that it's going to be a continuous load, we need to remember to do our 125% rule for continuous loads. So we take our original known load, multiply it by 1.25, and that gives us a new known load of 75 amps to size our wire by. And remember, our wire must meet or exceed the known load. We head to our primary ampacity table. We head to the copper side because it wants copper conductors. We're in the 75 degree C column, and we need to go down and find a wire that meets or exceeds 75 amps, and we find that it happens to be a number 4. Let's get to it. What size copper conductors would you select for a 40 amp load that's considered a continuous load using THHN type wire terminating on 75 degree C terminals? Step 1, find the total connected load. In this case, our starting known load is 40 amps. Well, we have to check for demand factors, but they've already let us know that it's going to be considered a continuous load. We take our original known load, multiply it by 1.25, and that gives us a new known load of 50 amps. And all of our wire must meet or exceed the known load. We head over to our primary ampacity table. We're going to start on the left-hand side because they want copper conductors, and we're in the 75 degree C column. We come down and we find a wire that meets or exceeds our load, and we're going to put it on a number 8. Great job. What size aluminum conductors would you select for a 90 amp load running for more than 5 hours using THHN type wire terminating on 75 degree C terminals? Step 1, find the total connected load. Well, our starting known load is going to be 90 amps, but we must check for demand factors. In this case, we find out it's a continuous load. We're going to do our continuous load math. We take our starting known load multiplied by 1.25, and that's going to give us a new known load of 112.5 amps. Now, we have to remember that all of our wire must meet or exceed the known load. We head to our primary ampacity table, but this time we have to be careful because they are wanting aluminum conductors. So we're actually going to start on the right-hand side of this table. We're going to start on the right-hand side. We're in the 75 degree C column. We come down and we find a wire that meets or exceeds the known load, and we find out that it needs to be on a 1/0. Let's get to it. That's the end of lesson 9.2. You can head over to electricalexamcoach.com to get the quizzes that go along with these videos and unlimited access to our testing center. I am the electrical code coach, and I want you to know that you're doing a great job. If you need anything from me, you can always just email me at electricalcodecoach@gmail.com. Don't give up. I know you can do it. Keep grinding. Let's get to it. Hey everyone, welcome back. I am the electrical code coach from electricalexamcoach.com. And this is lesson 9.3 in our video series. In this lesson, we're going to be sizing the overcurrent protective device and the wire in the same question for all of these loads, for continuous and non-continuous. Let's recap very quickly. If the question states that it's terminating to 60, 75, or 90 degree C terminal lugs, you're going to make your selection from that respective column under normal circumstances. With both OCPD and wire sizing, we still have that 125% demand factor for all loads that are expected to run for 3 or more hours. And we will always select the overcurrent protective device first, and then we'll choose our wire size. And it'll make more sense why we do that once we start sizing services in the next lesson. And once we get into larger amperage questions like 1,000 amps or greater, which we'll learn in the lesson after that one. Let's get to it. What size copper conductors and overcurrent protection would you select for a 54 amp load using THHN type wire terminating to 75 degree C terminals? Step 1, we're going to find our total connected load. In this case, we have it. It's 54 amps. But we must check for demand factors. Well, they've not mentioned a specific piece of equipment or that it's going to run for 3 or more hours. So in this case, there are no demand factors. Now, what we're going to do is size our overcurrent protective device first. You always size that first. So we head to our overcurrent protective device table, which is 240.6a for a 54 amp load. We're going to go down and choose the next standard size up. In this case, it's going to be a 60. Now, let's head and size the wire. For that, we're going to head to our primary ampacity table. We're going to start on the left-hand side and make sure that we're on the copper side because our question asks for copper. And we're in the 75 degree C column in this case. We're going to slide down and find a wire that covers the known load of 54 amps. And we're going to select a 6-gauge wire on a 60 amp overcurrent device. Let's get to it. What size copper conductor and overcurrent protection would you select for a 62 amp load using THHN wire terminating to 75 degree C terminals? Step 1, find our total connected load. In this case, it starts at 62 amps. But we must check for demand factors. With there being no special pieces of equipment mentioned or the fact that it's running for 3 or more hours, in this case, there are no demand factors. Now, we go ahead and size our overcurrent protective device. We head to our table with a 62 amp known load. And we're going to choose the next size up, which puts it on a 70. Now we can size our wire. For that, we're going to head to our primary ampacity table. We're going to be sure to start on the copper side because it's asking for copper. We're in the 75 degree C column. We slide down and find a wire that can cover the known load. And we find out that we're going to have a 6-gauge wire on a 70 amp breaker. Let's get to it. What size copper conductors and overcurrent protection would you select for a 105 amp load using THHN type wire terminating to 75 degree C terminals? Step 1, we're going to find the total connected load. Our starting known load is 105 amps, but we must check for demand factors. It doesn't mention a specific type of equipment or for how many hours that it's running, so in this case, there are no demand factors. First thing we're going to do is size our overcurrent protective device. For that, we head to table 240.6a and choose the next standard size up. And this is why it's very important for you to always go to the table and not just go off of memory or what you might do out in the field. Because out in the field, you might say, oh, this needs to be on a 125 because 125 is a common number. But how many of you know that there's actually a 110 amp breaker in between 100 and 125? I've seen them, I've worked with them out in the field, but they're not very common. Usually out in the field, we'll jump from a 100 to a 125 for like sub-panel sizing. But you have to be careful here. Always go to the table because the correct answer for this question is actually a 110 amp breaker. Now, let's size the wire. For that, we head to our primary ampacity table. The known load's 105 amps. We're on the copper side of the table because that's what the question said. We're in the 75-degree C column, and we go down and find a wire that covers the known load, 105 amps, and we're going to end up with a number 2 wire on a 110 amp breaker. Great job. What size copper conductors and overcurrent protection would you select for a 105 amp load expected to run for 3 or more hours using THHN type wire terminating to 75-degree C terminals? Step 1, find the total connected load. 105 amps is our starting known load, but we must check for demand factors. When we look, we find that we have the 125% continuous load rule, so we do our math. We take our original starting known load, we multiply it by 1.25. That gives us a new known load of 131 amps. And now we can size our overcurrent protective device. We head to table 240.6a and we choose the next standard size, which is a 150. Now we can come back and size the wire. We head to our ampacity table. We're on the copper side, 75-degree C column. We're going to go down and we're going to find a wire that covers the known load. And we're good to go. We're going to select a 1/0 on 150. Let's get to it. What size copper conductors and overcurrent protection would you select for a 50 amp load expected to run for 3 or more hours using THHN type wire terminating to 75-degree C terminals? Step 1, we're going to find the total connected load. Our starting known load is 50 amps, but we must check for demand factors. We see that it's a continuous load, so we're going to have our 125% rule. We take our starting known load, multiply it by 1.25, and that gives us a new known load of 62.5. Now we can size our overcurrent protective device. We head to our table, we choose the next standard size, which in this case is going to be a 70. Now let's size our wire. Heading to our primary ampacity table, we're going to be on the copper side of the table in the 75-degree C column, and we find a wire that meets or exceeds the known load. When we do, we find that it needs to be a 6-gauge wire on a 70 amp breaker. Great job. This is end of lesson 9.3. You can head over to electricalexamcoach.com to check out our pro version. I am the Electrical Code Coach, and my bargain is that these videos will add value to you, and you will in turn go out and add value to others. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach, and this is lesson 2.3 at electricalexamcoach.com. Today we're going to be learning about fixed appliances and how they work into a whole house load calculation. Fixed appliances include things like dishwashers in this picture, but it also includes things like garbage disposals, water heaters, central vacuum systems, and microwaves, and pretty much any other appliance once it's fixed. You'll notice in this bottom right-hand picture that there's 2 microwaves. One is not fixed, and the other one is fixed. And when you fix it to the wall or fix it so it can't move, either with plumbing or mechanical vents or anything else, it now becomes a fixed appliance, and there's a special way that they calculate them when doing a whole home load calculation. What it does not include is it does not include dryers or ranges. We're actually going to deal with those separately. So this includes all other fixed appliances except for dryers and ranges. Let's get to it. Before we dive into the calculations, let's learn about demand factors. We're going to be using them for the rest of the program. A demand factor is a multiplier that the code will use to decrease or increase the total calculated demand. The question is, will they use all 4 of these appliances at the same time? And the answer is no. So the code makers have made it so we can reduce the overall demand. Instead of just counting them watt for watt, they've made some multipliers that allows us to reduce the demand that we calculate. And remember, if we have less amps, we could have a smaller service. If we have smaller service, we could have smaller pipe, smaller wire, and a smaller overall cost of the job. The small appliance 75% rule works like this. Where 4 or more appliances are fixed in place, you can apply a 75% demand factor to the total calculated load of the appliances. I do want to note again that this excludes dryers and ranges. We're going to learn how to calculate those separately later in the program. So let's imagine that we have these appliances. And the question is, how do we calculate them all together to turn it into amps and later size our service, which sizes our wire and our pipe? What we're going to do first is find our total connected load. So we're going to go ahead and total all these up, and that equals 6,800. Then we're going to stop and check for demand factors. Step one in all load calculations is to get the total connected load. Then we're going to check for demand factors. And in this case, we can apply the 4 or more 75% rule. We take 6,800 multiplied by 0.75, and that gives us a new reduced load of 5,100 watts. And that's what we would take and add to our whole home load calculation. How many VAs would you calculate for a single family dwelling that has the following appliances: a 4,200 VA water heater, a 1,000 VA disposal, and an 1,100 VA dishwasher? First, we're going to find the total connected load. We total all that up. It equals 6,300 VAs. Now, we check for demand factors. In this case, we only have 3 appliances, so the 75% rule does not apply, and all we have to do is take our total. I do want to note that one of the 4 choices was as if you had incorrectly applied the 75% rule. In this case, because we only have 3, we don't apply any demand factor at all, and we take the total connected load at 6,300. Great job. How many VAs would you calculate for a single family dwelling in Dallas, Texas that has the following appliances: a 4,200 VA main water heater, a 3,500 VA additional water heater for the basement, a 1,000 VA disposal, and an 1,100 VA dishwasher? First, we're going to find our total connected load. We take and total it up, and it equals 9,800. Now, we check for demand factors. Sure enough, we have 4 or more fixed appliances, so we can apply the 75% rule. We take 9,800 multiplied by 0.75. That gives us a new reduced load of 7,350 VAs. I want to note that if you look at option B, it was 9,800, as if you didn't apply the 75% rule. You got to be careful. Oftentimes, they'll have one of the answers be as if you missed or added one of the steps that you shouldn't have. But you've been grinding. You're going to get it. I know you can do it. And we're going to select C. Let's get to it. All right, y'all, that's it for lesson 2. You can head over to electricalexamcoach.com to unlock the pro version and all of the quizzes and practice tests. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. And today we're going to be diving into dryer load calculations. We're going to be in section 220.54 and looking at table 220.54. Let's head there now. When we get to table 220.54, we're always going to read our black bold heading to make sure we're in the right table. Great, I feel like we are. We're going to start on the left-hand side and find our number of dryers. Then we're going to use a straight edge and come over and find our demand factor in percentage. I want to make an important distinction at this point in the program. You have to be very careful with these titles right here. Sometimes they're listed in a replacement value and it just says demand. And in other tables, it'll say a demand factor in percentage. And we've learned that that is just a multiplier. Section 220.54 lets us know that dryers must be calculated at a 5,000 VA minimum or the nameplate rating, whichever is greater. Now, let's learn what a nameplate is. Equipment nameplates. A plate mounted on the equipment or engraved in the equipment that is stating its voltage, amperage, horsepower, and or its wattage. Now, it may only have a few of these, but as we've learned in previous lessons, we can apply Ohm's law to find the unknown. Now that we're dealing with larger wattage appliances, we want to make something clear before we move on. We remember that 1 VA is equivalent to 1 watt, but what is a kVA? In our testing, it's the same as a kW, which is a kilowatt, which equals 1,000 watts. So it's true to say that 1 kVA is 1 kW for all of our testing. Now let's imagine that we have a dryer, and this dryer is a 5 kW. Well, it's also true to say that it's 5,000 watts. And at the same time, if they say that it was 5 kVA, it's also true to say that it's 5,000 VAs. Let's practice converting back and forth very quickly. Let's go from kVA to VA. So if we had 5 kVA and we wanted to go to VA, all we would have to do is take and multiply by 1,000, and that would equal 5,000 VAs. And the same if we wanted to go from VA to kVA, all we have to do is divide by 1,000, and it'll convert it over to kVA. You'll get very familiar with this and won't have to do any multiplying or dividing, but if you ever forget, that's all that you have to do. What is the total VA load you would calculate for one dryer with a nameplate rating of 4,500 watts? First, we find the total connected load. For this, we know that we have to do a 5,000 minimum or the nameplate, whichever is greater. So the 4,500 is gone and the 5,000 remains. Now, we check for demand factors. For this, we're going to head to table 220.54. And we're going to find that 1 through 4 dryers, it's at 100%, meaning that there is no demand factor. And we just select A. Great job. What is the total VA load you would calculate for one dryer rated at 5,200 VAs? First, we're going to find our total connected load. We know that we have to do a 5,000 minimum or the nameplate, whichever is larger. In this case, the nameplate's larger, so we're going to select 5,200. Now that we have our total connected load, we're going to check for demand factors. For this, we head to table 220.54. When we get there, we find that for 1 to 4 dryers, it's calculated at 100%. There is no demand factor. And we're going to select C. What is the total VA load you would calculate for one duplex with one dryer in each unit and a nameplate rating of 4,800 watts per unit? First thing we're going to do is we're going to find the total connected load. We know that it's a 5,000 minimum or the nameplate, whichever is larger. So the 4,800 is out and the 5,000 is in. Then we have to multiply it by our 2 units, and that gives us 10,000. Now we check for demand factors. For this, we head over to table 220.54. And we're going to find that 1 through 4 ranges is calculated at 100%. And we're going to select A. What is the total VA load you would calculate for an 11 apartment multifamily dwelling unit with one dryer per unit and a nameplate rating of 5,000 watts? First, we're going to find our total connected load. We know that it's a 5,000 minimum or the nameplate, whichever is larger. We take our 11 units, multiplied by 5,000, and that equals 55,000 VAs. Now, we check for demand factors. We head over to table 220.54. When we get there, we find the demand factor for 11 is 47%. So we take our original load, multiplied by the demand factor, and that gives us a new reduced load of 25,850 VAs. And we're going to select C. Great job. What is the total VA load you would calculate for a 17 apartment multifamily dwelling unit with one dryer per unit and a nameplate rating of 5,000 watts? First, we're going to find our total connected load. We're going to use 5,000 minimum or the nameplate, whichever is larger. We take our 17 units, multiplied by 5,000 each, and that gives us 85,000 VAs. Now, let's check for demand factors. When we get to table 220.54, we're going to find that it's a 47% base minus 1% for each dryer past 11. So what we do is first have to figure out how many dryers we are past 11. We have 17 dryers minus the 11 base, and that lets us know that we're 6 past 11. Well, what this code is stating is that 47% was our base multiplier, and then what we're going to do is minus 1% for each one that we are past 11. We were 6 past 11, so we're going to take our 47% base minus 6, and that's going to give us a new demand factor of 41%. Now, all we have to do is multiply. We take our original load, multiplied by 0.41, and that gives us a new reduced load of 34,850 VAs. And we're going to select B. Great job. That's the end of lesson 3.1. I want to encourage you and let you know that you're doing a great job and that you can do it. You can head over to electricalexamcoach.com to unlock all of the features in the Pro version, including flashcards and practice quizzes. I want to let you know that I offer coaching 100% for free. All you have to do is just email me at electricalcodecoach@gmail.com. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 3.2 in our video series. Today we're going to be learning about how to calculate ranges and cooking equipment and how they fall into the whole house load calculation. We're going to be in section 220.55. We're also going to be in table 220.55. Let's get to it. When we get to table 220.55, we're going to read the black bold heading at the top of the table to make sure that we're in the right table. Then, starting on the left-hand side, we're going to find our number of ranges. 1, 2, 3, 4, 5, and so on and so forth. Then we're going to notice that there's 3 different columns. They're really in 2 different groups. It's column A and column B are grouped together under the demand factor in percentage column. And the reason that's so important for us to watch out is because column A and column B are multipliers. They're actual demand factors. But column C is a replacement value, and you'll understand more of what that means as we get farther through this video. Starting on the left-hand side in column A, this is when your individual range falls 3.4 or less kWs. In column B is when our ranges, the individual range itself, falls in between 3.5 and 8 3/4. Then column C is when our ranges are 8.76 through 12 kW. Then in the bottom left hand of the table, you're going to see some notes. And that's when we have a situation that doesn't fit into the normal table. And we're going to take it piece by piece. Let's get to it. How many VAs would you calculate for a 9 kW range in a single family dwelling? The first question we're going to ask is, what column does our individual range fall in? Well, ours is a 9 kW, so it's going to fall into column C because it's greater than 8.76, but not over 12. And column C is a replacement value. Now let's find our total connected load. On the left-hand side, we're going to find our number of ranges. In this case, it's 1. Then we're going to cross all the way back over to column C and find that our replacement value is 8 kW. Then, just to stay in practice, I want you to always be familiar with checking for demand factors. But in this case, in table 220.55, column C is a replacement value. It is not a multiplier, so we're just going to select C. Great job. What is the total VA load you would calculate for 3 kW ranges in a dwelling unit? First question we're going to ask is, what column does our individual range fall in? Well, ours is going to fall into column A because the individual range is 3 kW. So we know that we're going to be doing a demand factor. Now we can start from the beginning. First, find our total connected load. We take our 3 multiplied by 3 kW, and that equals 9 kW. Now we check for demand factors. We're going to start on our left-hand side of the table. We're going to find our number of ranges. Then we're going to come over and we're going to find our demand factor. And we find that the demand factor for 3 ranges in column A is 70%. Now, all we have to do is multiply. We take our 9 kW multiplied by our demand factor. That gives us our new reduced load, and we're going to select B. What is the total connected load you would calculate for 2 3.2 kVA cooking appliances in a dwelling unit? First question we're going to ask is, what column does our individual range fall in? Ours falls into column A. Now let's find our total connected load. We take and multiply it out, and we end up with 6.4. Now let's check for demand factors. When we do that, we start on the left-hand side of our table. We come over and find our number of ranges, and then we cross over, and we find that for column A, 2 ranges is 75%. Now, all we have to do is multiply. We take our 6.4 multiplied by our demand factor, and this gives us our new reduced load, and we're going to select A. Great job. What is the total VA load you would calculate for 1 7 kVA range in a dwelling unit? First off, let's find out what column we're using. Our individual range falls into column B. Now let's find our total connected load. Well, in this case, it's just 1 range, so the total connected load is 7. Now let's check for demand factors. When we head back to our table, we're going to start on the left-hand side and find our number of ranges. Then we're going to cross over and find our multiplier. And when we do that, we find that it's 80% for 1 range. Now let's do the math. We take our 7 multiplied by our demand factor, and that gives us our new reduced load. And we select C. How many VAs would you calculate for a 14.6 kVA range in a dwelling unit? Step 1, find out what column our individual range falls in. When we get to column C, we find out that it's only good through 12 kW. When it's over 12 kW, we have to use one of our table notes listed down below the table. In this case, we're going to be using note 1. Note 1 says that when you have ranges that are 12 through 27 kVA, what we're going to do is increase that column C value by 5% for each kW that we are past 12. Now that sounds really complicated, but I'm going to break it down piece by piece. Step 1 is find your total connected load. In this case, it told us to increase the column C value by 5%. So we start on the left-hand side and find our number of ranges, which is 1, and then we cross over and find the column C value, which is 8 kVA. It wants us to increase that number by 5% for each kW we are past 12. Well, we're 14.6 past 12. And what the code states is that you're going to increase it for each kW past 12 or major fraction thereof. That's just a fancy way of saying if it's 0.50 or greater, you're going to round up. If it's 0.49 or less, you're going to round down. Well, in this case, we're 0.6, so we're going to round up to 15 kVA. So we are 15, and we need to find out how many we are past 12. Well, to do that, we can do some simple math. We have 15. We need to minus the 12 base, and we have 3 left over. Then we need to take that 3 and multiply it by 5% for each one, which is a total of a 15% increase. We're going to take our original number from column C, and we're going to increase it by 15%, and that's going to give us 9.2 kW. The reason that I put the 1 in front of it is because that brought back the 8, and we increased the 8 by the 15%, and it gave us 9.2. And we're going to select A. Great job. What is the total VA load you would calculate for a 3 kVA cooktop and 2 4 kVA wall-mounted ovens in a dwelling unit? First thing we're going to ask is what column do the individual ranges fall in? Well, in this case, we find that it falls into column A and B. This question is very simple. All you have to do is treat the column A ranges individually, the column B ranges individually, and then total them together. So what we do is we find our total connected load. The column A ranges is just 1, so it's 3 kVA. The column B ranges, we have to do some math, and we end up with 8 kVA. Now, we check for demand factors. We head back to our table, and we start on the left-hand side for our column A ranges, and we find the multiplier for 1, and then we start on the left-hand side and find our number of ranges for our column B ranges and find the multiplier, and we're going to find that they're 80 and 65% respectively. Now, all we have to do is do the math. We take our column A ranges and do the math, take our column B ranges and do the math, but then we can't forget to total them back together, and we're going to select A. Great job. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. Today we're going to be calculating HVAC VAs for our heating, venting, and cooling. The only code that we need to be familiar with is 220.60, and that's talking about non-coincidental loads. Let me explain what I mean. Usually in a typical house, you're not going to be running the heating and the cooling at the same time. So the code has made provisions for our whole house load calc that we only have to count the larger of the two. Let's get to it. How many VAs would you calculate for an 18.2 amp air conditioner compressor with a 1.8 amp blower and a 10 kW heat strip rated 240 on a dwelling unit? First thing we're going to do is find our total connected load. Let's do our air conditioning first. We take our 18.2 amps and then we add it with the blower motor. That's going to give us 20 amps. Now to convert that over to VAs, all we have to do is multiply. 20 amps multiplied by the voltage gives us 4,800 VAs. Now let's do the heat. We have 10,000 to start with, but then we need to add the blower motor. Our blower motor is 1.8 amps multiplied by 240. That gives us another 432 VAs, and then we total the two together. Now we check for demand factors. There are no demand factors on this, and we will just select the larger of the two, and in this case, it's going to be the heat. We select C. Great job. How many VAs would you calculate for a 28.2 amp air conditioner compressor with a 3.2 amp blower motor and a 6 kW heat strip, all rated 240 on a dwelling unit? First, let's find our total connected load. Let's do our AC first. We take our amperages and we add them together. Then we need to take and multiply that by the voltage to convert it over to watts. And we end up with 7,536. Now let's do our heat. We know that we had 6 kW to start with. Then we need to add our blower motor. We take our blower motor at 3.2 multiplied by the voltage, and that gives us another 768 VAs. We total those two together, and we check for demand factors. There are no demand factors on this part of the code, so we're just going to select the larger, and in this case, we're going to select the cooling. Great job. That's the end of lesson 4.1. You can head over to electricalexamcoach.com to unlock the pro version and all of the practice quizzes. I'm here anytime you need me for free coaching. It's electricalcodecoach@gmail.com. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 4.2 in our video series. Now we're going to learn how to apply the demand factor to the general lighting load. At the beginning of the program, we learned that it was 3 VAs per square foot, and we had to add on the 4,500 VAs for our 2 small appliance and 1 laundry circuit. At the beginning of the program, I did not teach you about the demand factor for this because it's kind of complicated at face value, especially if you don't know what a demand factor is. But now that we're this far in the program and you are very familiar with using demand factors, I'm going to teach it to you now. And for this one, we're going to head to table 220.42. It's a very important table in our load calculation process. When we get to table 220.42, we always read the black bold heading to make sure that we're in the right table. And it says demand factors for lighting. Now, you can ask the question, if this is the 3 VAs per square foot, well, it includes receptacles. And you are correct. We are allowed to use this table for commercial lighting or any of the lighting in the following locations that we're getting ready to talk about. But we're also allowed to use it for the entire 3 VAs per square foot, plus the 4,500 that we tacked on for the 2 small appliance and 1 laundry. Using this table, we start on the left-hand side and find our location. The first one we find is dwelling units. Then we're going to find hospitals, hotels and motels, warehouses, and really important down here at the bottom, it says all others. So if it's not listed inside of this type of occupancy, we're going to cross over. And if you look over here down in the bottom right hand, it's at 100% calculation, meaning that there is no demand factor for lighting unless you're one of these specific places that are listed on the left. Then over here across the top, we find our demand factor. In this column, it's the portion of the VAs. And then in this column, it is the demand factor in percentage. We're going to break this down one piece at a time and learn how we apply the demand factor to the 3 VAs per square foot and the 4,500 VAs for the small appliance and the laundry circuit. Let's get to it. When looking at this table, we're going to see a multi-layered demand factor for dwelling units. Step 1, we're going to take the first 3,000 VAs at 100%. Step 2, we're going to take in between 3,001 through 120, which is technically just another 117,000 more. And that's how I'm going to refer to it for the rest of the program. We're going to take that percentage at 35%, and then we're going to take anything above and beyond that at 25%. Then step 3, we add them back together. We take the original 3,000 that we set to the side. Then we're going to take that new reduced load, add those two together, and that's going to give us our total load. What is the total general lighting load you would calculate for a 1,600 square foot home, including the small appliance circuits and the laundry circuit in a dwelling unit after demand factors? I want to note that on your examination, they will not mention the small appliance and the laundry circuits. You just have to know that anytime you're doing the total general load or you're doing a whole house load calc, you have to tack on that 4,500 VAs. Step 1, find our total connected load. We're going to take our 1,600 square foot multiplied by 3 VAs per square foot, and that equals 4,800 general square foot VAs. Now we need to tack on our 4,500 for our 2 small appliance and 1 laundry circuits. Then we take that load and we check for demand factors. We head to table 220.42. We're going to take our first 3,000 at 100%. Then we're going to take that remainder at 35%. Then all we have to do is total the two back together. And we're going to select D. Great job. What is the total general lighting load you would calculate for a 1,200 square foot dwelling unit? Notice that I took out all the pointers that we had in the previous slide. Anytime it asks for the total, you're always going to be applying a demand factor if there is one. And in every one of these type calculations, you're going to have the 2 small appliance and 1 laundry circuits. Step 1, find the total connected load. We're going to take our 1,200 square feet multiplied by 3 VAs per square foot, and that's going to give us 3,600 square foot VAs. Now we have to tack on our 4,500 for our 2 small appliance and 1 laundry circuits. 3,600 plus 4,500 equals 8,100. Now we check for demand factors. We head to table 220.42. Step 1, we're going to minus 3,000 and take it at 100%. Step 2, we're going to multiply that by 0.35. All we have to do now is add them back together, and we end up with a new reduced load of 4,785 VAs, and we select A. Great job. That's the end of lesson 4.2. You can head over to electricalexamcoach.com to unlock all the quizzes, flashcards, and everything else that comes with the pro version. I offer my coaching 100% for free. All you have to do is email me at electricalcodecoach@gmail.com. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com, and this is lesson 4.3 in our video series. And today we're going to be tying all these pieces together that we've been learning about the whole home load calculation. We're going to learn how to take our general, our fixed appliances, our dryer, our range, our HVAC, and turn it into our whole home demand. Let's get to it. What is the total VA demand you would calculate for a 1,600 square foot home with the following loads? Now, I know this looks daunting, but we're just going to take it one piece at a time. You've worked very hard up until this point, and I know you can do it. I want us to get used to laying out all of our calculations like this. On our piece of paper, write general, fixed appliances, dryers, ranges, and HVAC, and we're going to fill them in one at a time. Step 1 is to find our general lighting and receptacle loads. We're going to first find our total connected load. We take our 1,600 square foot multiplied by 3. That gives us 4,800 square foot VAs. Now we add on our 2 small appliance and 1 laundry circuit, which is 4,500. That gives us this total connected load of 9,300. Now we check for demand factors. Step 1, we're going to take the first 3,000 at 100%. We're going to take that remainder at 35%. Then we take the 2 and total them back together. And we're going to put that over here on the right-hand side. Every time I want you to write it out just like this, add in each load, total them up, and you'll be on your way to doing the whole house. Let's get to it. Now let's do our fixed appliances. We have a garbage disposal, dishwasher, and water heater. Find the total connected load. We total them all up, and it equals 5,500. Now we check for demand factors. There are only 3 appliances, so the 4 or more 75% rule does not apply, and we write down 5,500. Now we deal with our dryer in the same way. We find our total connected load. We know that it's 5,000 minimum or the nameplate, whichever is larger. Now let's check for demand factors. When we get to table 220.54, we find that 1 through 4 dryers are calculated at 100%, and we put down 5,000. Now our range. First thing we're going to ask is what column does our individual range fall in? Well, this one falls into column C, and column C is a replacement value. Let's find our total connected load. We start on the left-hand side of the table. We find our number of ranges, and then we cross over to column C, and it's 8,000. Now we check for demand factors. There are no demand factors on column C because it is a replacement value, and we write down 8,000. Great job. Now for our HVAC VAs, we're going to take the larger of the heating or cooling. First, find our total connected load. Our heating is 10,000, and our cooling is our amps multiplied by our volts, which equals 4,320. Now we check for demand factors. There are no demand factors on this portion, so we're just going to select the larger of the 2, and we're going to put down 10,000. Now all we have to do is total it all together. Now all we have to do is total all of our loads. Make sure that you push the equals button in between each addition. And the reason is sometimes when you add a bunch of numbers without clearing it out, it will mess up inside the calculator. So I'm going to do mine like this. 5,205 plus 5,500 and then I'll hit the equals button, and then I'll do plus 5,000, plus 8,000, plus 10,000, pushing the equals button in between each time just to make sure I end up with the right answer. Then I'm always going to double check my answer on these large calculations and make sure that I get the same number twice. We end up with 33,705, and we select A. Hey everyone, welcome back. I am the Electrical Code Coach from electricalexamcoach.com. This is lesson 6.1 in our video series. Today, we're going to be learning all about box fill. We're going to be in section 314.16, and we have two primary tables that we're going to be using. The first one that we're going to cover is 314.16a. Let's get to it. On the left-hand side is going to be our box size in inches. The next column over is going to be the type of box, and there are several different types of boxes. The first one is going to be the round octagonal box. A round box is truly circular, and the picture listed here is actually an octagonal box. I want to give a shout out to homedepot.com. It's where I snagged all these pictures. The next three lines you'll notice say square, and these boxes are true 4-square boxes. They're 4 by whatever the depth is. And if you look back over here to your dimensions where the box size in inches is listed, this box states that it's a 4 by 4 by whatever the depth is. There are 3 different depths. The next 3 lines you'll notice say square as well, but its dimensions are a little bit different. It says 4 11/16 by 4 11/16 by whatever the depth is. Down below there start your device boxes in all different shapes and sizes. Finally, we come to our masonry boxes. Listed below there, you're going to see different type of raised covers, which also give you a little bit more cubic inch volume inside of your box. The next column that we need to pay attention to is this middle one right here. Now, in the NEC, it actually says a minimum volume, which is kind of deceptive to the installer because it's actually your maximum volume that you're allowed to fill that box. And it's listed in cubic inches. That's all we're concerned with. We're not concerned with any metric designators inside of this table. We want to be dealing with cubic inches. And the reason it's cubic inches is because we have 3 different measurements. We have 4 by whatever the depth is. In this column, you're going to find the maximum that you're allowed to fill each box. Then when we come over here to the far right of the table, it's one of my favorite pieces. It's actually like a cheat sheet. If all of your wires are of the same size, you can use this part of the table and make it very simple on yourself. First thing you'll do is you'll come over and find your gauge of wire. Then you'll come over here and find your type of box, and then come over and tee off with how many wires can fit inside of that box. It's very simple. Now let's look at the second table that we're going to be dealing with for box fill. And it's right below there. It's 314.16b, and this one's very simple to understand. On the left-hand side is our conductor size, and on the far right-hand side is going to be our cubic inch volume. Every box can only handle so many wires and devices, and that's what we're going to learn in this lesson here today. Each box has so many cubic inches that you can fill, and each conductor and device takes up so many cubic inches of that box. Now, let's do some practice questions and get to it. What size round octagonal box would you select for 9 number 12 conductors? For this one, we're going to be using table 314.16a. We're going to start here and we're going to find our gauge of wire. Then we're going to come down and we're going to find a box, making sure to cross over and double check that we don't crest over into a different style box. We want to stay in the round octagonal. We find our conductors, we find the one that fits it, we slide over and double check ourselves, and we're going to select A. Great job! What size round octagonal box would you select for 7 14 gauge conductors? We're going to head to table 314.16a. We're going to start here on the right hand side and we're going to find our gauge wire. Then we're going to come down and find a box that fits it and be sure when we cross over that we stay in the right category of box, and we're going to select C. What size 4-square box would you select for 8 number 8 conductors? We head to 314.16a. We're going to start here on the right-hand side, and we're going to find our size wire. Then we come down and make sure that we're in the right type of box. We cross over, and we're going to find that it's A. How many number 10 conductors can you fit inside of a 4 11/16 by 1.5 inch square box? It's the same process, just looking at it differently. We're going to go ahead and come to our table, 314.16a. We're going to find our gauge conductor. We're going to come down and find our box. Make sure we cross back over, and we find that we can fit 11 inside of this box. How many number 8 conductors can you fit inside of a 4 by 2 1/8 by 1.5 inch device box? We head to 314.16a. We're going to find our gauge wire. Then we're going to come over and find our type of box and size, make sure we do everything correctly, and we're going to find that it holds 3. What is the maximum cubic inch volume for a 3 3/4 by 2 by 2.5 masonry box? For this one, we're going to head to 314.16a, and we're going to use that middle column, that volume column, and we want to find out how many we can do. We come down, we look very closely, and we find that it's 14 cubic inches. This is very important that we understand this process before we move on into more complex box fill calculations. What is the maximum cubic inch volume for a 4 11/16 by 1.5 inch square box? We're going to use the same process. We head to our table. We're going to go to that volume column, and we're going to come down and find our correct type of box, and we're going to find that it's 29.5 cubic inches available area to fill. How many more number 10 conductors can you fit inside of a 4 11/16 by 1.5 inch square box that already contains 6 number 10 conductors in it? Well, since both of these are of the same size, we can just do some simple math. First, we have to find out how many the box holds at all. And we go in and we find that it holds 11. Then we have to do some simple math. We already have 6 conductors, so we take our original 11 minus 6, and it lets us know that we can put 5 more inside of that box, and we select A. How many more number 12 conductors can you fit inside of a 4 by 2 1/8 by 2 1/8 device box that already contains 5 number 12 conductors? For this one, we're going to head back to our table 314.16a. First, let's find out how many wires it can hold originally. It can hold 6. We already have 5, so we take 6 minus 5 equals 1, and we can put 1 more conductor inside of this box. What is the cubic inch volume for a number 6 conductor? For this one, we're going to head to 314.16b. We're going to start here on the left-hand side of the table and find our size conductor. Then we're going to come over and we're going to cross over to our cubic inch volume, and we're going to select D. Great job. What is the cubic inch volume for a number 12 conductor? Head back to 314.16b, start on the left-hand side and find our size conductor, then cross over to the cubic inch volume, and it's stating that for every number 12 that's in that box, according to the count, which we're getting ready to learn, takes up 2.25 cubic inches of that box. Let's get to it. What is the total cubic inch volume you would calculate for 4 12-gauge conductors and 3 14-gauge conductors? First thing we're going to do is head to our table. Now we have to do some simple math. Let's grab all of our 12-gauge conductors first. We have 4 of them. Multiply it by 2.25. That equals 9 cubic inches. Now let's snag our 14s. We take 3 multiplied by 2, and that gives us 6 cubic inches. But now we can't forget to add them back together. Total it all up, and these conductors are taking up 15 cubic inches of this box, and we're going to select C. What is the total cubic inch volume for 3 10-gauge conductors and 5 8-gauge conductors? We head straight to our table. We do some math here. We bear out the 10-gauge conductors. Then we bear out the 8-gauge conductors. We total those two back together, and we find that it's taking up 22.5 cubic inches, and we select B. What is the smallest device box you could use to fit 4 12-gauge conductors and 3 14-gauge conductors? For this one, we're going to be using tables A and B. Let's start over here in table B and get our total count. Then we'll go to table A and find which box fits it. We do the math on our 12-gauge conductors. We do the math on our 14-gauge conductors. These conductors are taking up 15 cubic inches. The code wants to know the smallest box that will fit it. So we come over here to our middle column, the volume column, and we slide down until we find a device box that just fits it. And we're going to find that it's a 3 by 2 by 3.5. What is the smallest round octagonal box you could use to fit 3 10-gauge conductors and 3 12-gauge conductors? For this one, we're going to be using both the tables again. Let's go ahead and bear all of our math out. And we find out that these conductors are taking up a total of 14.25. Now let's head over here to table A and go down the volume column until we find the right type of box, which is right up here at the top. The round octagonal boxes. Find the one that fits, and it's a 4 by 1.5 inches. Great job. Now let's learn about the rules for box fill. We're getting ready to cover a lot of ground, and this is something that you have to master. But don't feel like that you have to master it in one pass. Watch this part of the video over and over until you thoroughly understand it. We're going to learn how to count conductors now for our box fill calculations. We have to accommodate for each wire and then also for the different devices and fittings that we use out in the field. We're not going to be dealing with equipment grounding conductors at first. We're going to calculate those separately at the end of this slide. So now we're dealing with only neutrals and hots. Each conductor counts as 1 of whatever gauge it is. So each 12 counts as 1, each 10 counts as 1, whatever gauge wire it is. Each conductor that passes through the box counts as 1. So even if it doesn't terminate or splice inside that box, if it's passing through that box, it counts as 1 each. Each internal clamp only counts as 1 total based off the largest conductor that's in the box. Let me show you what I mean. This is an internal clamp. The clamping mechanism is inside the box. Well, it's taking up some of my space, so we have to account for it somehow. What this code is stating is it doesn't matter if I have 1 or 5 of these clamps, we're only going to count it as 1, and it's going to be grouped with whatever the largest conductor is in the box. Meaning if I have 12 and 10-gauge conductors inside that box, this internal clamp would count as 1 10-gauge conductor. All of the fittings we're going to convert over to conductors, then the conductors we're going to convert over to the cubic inches, and you'll know more of what that means as we go through this lesson. This is an external clamp because the clamping mechanism is on the outside of the box, and we don't have to count those at all for box fill purposes. Next, each stud or hickey that is present in the box shall count as 1 total based off the largest conductor that's in the box. Now, these are really old words, probably from the 30s if I had to imagine, but they still use them on examinations today. And this is what we're talking about. Imagine that we're hanging a chandelier. This we would call the stud or the nipple. Or, this would be the nipple, this would be a nipple. But they're calling this the stud and this a hickey. And they still use this terminology on exams today, so you definitely need to understand. In this scenario here, in this picture, the stud would count as 1 of whatever gauge was in the box that was the largest, and the hickey would count as 1 of whatever gauge was in the box that is the largest. And we're going to do lots of practice, so don't worry about it. Now we need to account for device straps and yokes. What the code states is that for each device strap or yoke, it's going to be counted as 2 based off the largest conductor that's connected to the device. As we learned earlier in the program, this is a device yoke or what we call a device strap. So each one of those, and how I like to think about it, is each gang of a box. If you have a single gang box, 2 gang box, or 3 gang box, each gang is going to count as 2 based off the largest wire that is connected to the device. So if I had a box that had 12 gauge on one switch and 14 gauge on another switch, the first switch would count as 2 12s and the second switch would count as 2 14s. Now let's deal with equipment grounding conductors. Let's deal with the 2017 first. If you are on the 2017 code, this is how you deal with equipment grounding conductors that are in the box. It's only counted as 1 total based off the largest conductor in the box. Meaning it doesn't matter if you have 10 equipment grounding conductors, they all only count as 1 for your count total, and it's based off the largest conductor that's in the box. So if I have 10s and 12s, it's only going to count as one number 10. Now in the 2020 and in the 2023, it's a little bit different. Up to the first 4 conductors, it's going to count as 1. Then for every one that is past 4, you're going to increase it by a 1/4 inch volume. And we're going to do some practice questions with these. Just let that soak in, and when we get to the practice questions, we're going to expound on it more. If you're still on the 2017, when I come to this part of the lesson today, I want you to just fast forward through it. You don't need to learn it. It will just confuse you. 2017 will come first, and the questions will state what year I'm dealing with. Then when we get to the 2020 and the 2023, I'll let you know, and that way you can learn your respective lesson. Let's get to it. What is the total cubic inch volume you would calculate for a light box that contains 3 12-gauge conductors with 1 stud and 1 hickey present in the box? For this one, we're going to go to table 314.16b. We know that each 12 is 2.25 cubic inches. Now let's count our conductors. We know that we have the 3 number 12s originally, but now we have to deal with the studs and the hickeys. Our code states that for each stud and each hickey, they count as 1 each based off the largest conductor that's in the box. In this case, we only have number 12s, so they're going to be grouped with the 12s. So that lets us know that we have a total of 5 number 12s. That's what I meant by we're converting everything back to conductors, and then we can do our multiplication. We take those 5 number 12s, multiply it by the cubic inch volume for 12, and we end up with 11.25 cubic inches, and we would select C. What is the total cubic inch volume you would calculate for a light box that contains 3 number 12 gauge conductors, 3 14 gauge conductors, and 1 hickey present in the box? We'll head to our table. We know that each 12 is 2.25, so you always deal with the largest conductors first. And the reason is because your fittings are likely going to be grouped with the largest conductors. We know that we have the 3 number 12s, but now we got to deal with our fittings. In this case, we have 1 hickey. Each hickey counts as 1 based off the largest conductor that's in the box. And what we're going to do is group it with the 12s. We have the 3 original conductors, the 1 fitting. We have 4 number 12s. We bear that math out and end up with 9 cubic inches. Now let's deal with our leftover conductors. We have 3 14 gauges. We take and bear all that math out. Then we total it together and we end up with 15 cubic inches that all of this is taking up in this box. This is something that you'll have to take your time and master. One of my favorite sayings is, you don't wake up on that level. You don't wake up understanding this. You don't watch the video once and get it. If it were that simple, anybody can do it. I hope it's been very easy for you to understand up until this point, but for you to truly master it, you got to get after it. What is the total cubic inch volume you would calculate for a box that contains 8 number 12 gauge conductors and 2 single pole switches in a 2-gang box? We look at 314.16b. We know that each number 12 is 2.25. Let's go ahead and count our conductors. Each device yoke counts as 2 based off of whatever wire is terminating to the device. We know we have 8 original conductors, and we only have 1 size wire, so we know it's going to get grouped with the 12s. And each one of those devices counts as 2, so we end up with 4 more number 12s, which gives us 12 12-gauge conductors. Now we take and do our math, we end up with 27 cubic inches, and we select B. What is the total cubic inch volume you would calculate for a box that contains 8 12-gauge conductors terminating to 2 single-pole switches, 6 14-gauge conductors terminating to 2 single-pole switches in a 4-gang switch box? This looks like a tough question, but I know that you can do it. First, we're going to head to our table so we can get our values. We know what each 12 is, and we know that each device yoke counts as 2 based off the largest wire that's terminating to the device. Let's go ahead and deal with our 12s. We know that we have 8 conductors and 2 devices for those 12s, so each one of those devices counts as 2 more, giving us a total of 12 12-gauge conductors. We take and bear the math out, and we end up with 27 cubic inches. Now we just do the same for the leftover devices. We have our 6 original conductors, And we have 4 more based off of our count because remember, it's based off the largest wire that terminates to that device. We take and bear that math out, total the two together, and end up with 47 cubic inches. Let's get to it. What is the total cubic inch volume you would calculate for a box that contains 3 internal clamps and 4 12-gauge conductors? We head to our table. We know what each 12 is. All internal clamps count as 1 total based off the largest conductor in the box. We only have 1 size wire in the box, so we're good to go. We take our 4 original conductors plus our 1 clamp count, and that equals 5. We bear our math out, and we select C. Now let's deal with equipment grounding conductors. In the 2017, all equipment grounding conductors just count as 1 based off the largest conductor in the box. 2020 and later, all equipment grounding conductors count as 1 based off the largest conductor in the box up to 4 conductors. So 4 conductors and under count as 1 total. But when you have over 4, there's going to be a 1/4 inch volume increase that's going to be added for each additional equipment grounding conductor after 4. I'm going to teach you how to do it one step at a time. What is the total cubic inch volume you would have for a box that contained 2 hots, 2 neutrals, and 2 equipment grounding conductors, all of the 12-gauge persuasion in the 2017? Well, we know we're going to count our 2 hots, we know we're going to count our 2 neutrals, and all of the equipment grounds count as 1 total. We would have a total of 5 cubic inches. We do the math for 12-gauge conductors, and we end up with 11.25. Let's do one more quick practice for the 2017. We got 3 hots, 3 neutrals, and 3 equipment grounding conductors, all of the same size. We're going to take those 3 hots, the 3 neutrals, and then all of the equipment grounds count as 1 total based off the largest conductor that's in the box. That gives us 7. Now we bear our math out, end up with 15.75, and we select D. Let's go ahead and do one more for the 2017. We have the total cubic inch volume, and we have 3 12 hots, 3 12 neutrals, 3 14 hots, and 3 14 neutrals, and 6 equipment grounding conductors in the box. First, let's count our 12s, because that's what we're going to group all the equipment grounding conductors with, is the largest conductor in the box. We know we got 3 hots, we know we got 3 neutrals, and we're going to group all of those equipment grounding conductors, counting them as 1 with the largest, which happens to be 12. We take and bear that math out. Now let's deal with the 14s. We had 3 hots, 3 neutrals, don't have to deal with any grounds, they've already been dealt with. We take and bear that math out, total the two together, and we end up with 27.75 cubic inches. Now let's move on to the 2020 and the 2023. What is the total cubic inch volume you would have for a box that contained 7 equipment grounding conductors, all of the 12-gauge persuasion in the 2020 and the 2023? I left out all other conductors because you're going to use the same rules in that after you do this calculation, you group it with whatever the largest conductor is in the box, like you learned previously. What we're going to do is we're going to count the first 4 and count it as 1. And then a 1/4 inch increase for each one past 4. Sounds complicated. We're going to break it down very simply. We have 7 total, and we're going to minus 4 because those first 4 we counted as 1. So we have 3 left over, and we're going to take those 3 and multiply it by 1/4, and that gives us 0.75. So we have a total of 1.75 conductors based off whatever the largest conductor is in the box. In this case, there's only number 12s. So we would take that 1.75, multiply it by the cubic inch volume for a number 12 conductor, and we end up with 3.9375 cubic inches for our equipment grounds. What is the total cubic inch volume you would have for a box that contained 6 hot conductors, 6 neutral conductors, and 6 equipment grounded conductors, all of the 12-gauge persuasion in the 2020 and the 2023? First thing we're going to do, we know we take the 6 hots and the 6 neutrals, and we're going to set that to the side. Now we got to deal with the equipment grounding conductors. We're going to, for the first 4, it's going to count as 1. So we need to figure out how many we are past 4. We have 6 total, minus that 4. That means we are 2 past 4. For each one of those, it's going to be a 1/4 inch increase. Take 2 multiplied by 0.25, that equals 0.50. Then we have our 1 original. Then we have 0.50 add-on. So that gives us 1.50 grounds. We need to take and add that back to the 12. So we take our 12 plus our 1.50. Then we multiply that by the individual volume for a number 12, which is 2.25. And we end up with 30.375. Let's get to it. All right, y'all, that's it for this lesson. You can head over to electricalexamcoach.com to unlock the Pro version and the Unlimited Testing Center. We also offer our full program on USB drive and DVD, so you can watch it offline and without commercials virtually anywhere. It also includes the MP3 files of all the lessons, so if you just want to listen to them as you drive down the road or while you're on the job site, you can do that. You can check out all that in the link in the description below. Most importantly, I want you to know that I offer 100% free coaching in life and in business. Just email me at electricalcodecoach@gmail.com. I just want to see you guys win. Let's get to it. Hey everyone, welcome back. I am the Electrical Code Coach. Let's go ahead and dive right into pipe fill. This first lesson is going to deal with if all the conductors are of the same size and insulation type, meaning if they're all number 12s and THHN. The next lesson, lesson 7.2, will deal with if we have different sizes of conductors and different insulation types, meaning if I have 10s and 12s inside of the same conduit. Let's go ahead and learn about the table that we'll use if they are all of the same size. We're going to use Annex C. And if you've tabbed your code book, you have an Annex C tab. And if you haven't tabbed it, you can just follow along. If the conductors are all of the same size and insulation type, we get to use like a cheat sheet